Well, hello everybody and welcome to this CasADi tutorial. How would we describe CasADi? We tend to say it's a tool that allows you to efficiently write your own dynamic optimization solvers or algorithms. And I hope you get a little bit of an idea with what I mean with this in this tutorial. CasADi is an open source project with a permissive license. It's written in C++ code. But it has a convenient interface to mainly Python. And we try to make the mapping of the interface and the underlying library one-to-one. So all features present in C++, you have them in Python and vice versa. We have quite a few of numerical backends that can be used to solve your optimal control problems. You need optimizers, of course, like general NLP solvers, and we have IPopt, Warp, and KNitro for these. For integration, we have the Sundial suite. CasADi was started in 2010 by Joel Anderson, a PhD student under Moritz Thiel, and then a bit later I joined in. My name is Joris Gillis, and then Greg came in later in development. So what is the outline of this tutorial? I will start with scalar expression graphs, SX, and then go to automatic differentiation and how CasADi uses this internally. I showcase how an integrator is constructed in CasADi. I move on to MX graphs, the matrix valued expression graphs. And then in the end I conclude with solving an actual optimal control problem in a couple of lines of code. So this demonstration is in the Python world. So let's start with importing CasADi. Next we will construct symbolic primitives, scalar symbolic primitives, and we do this with sx.sim. So sx stands for scalar expression. When we do this, we have an object in Python called x and y, and we can construct expressions with this using common mathematical operators. So if I just print z, you'll just get a copy of what we typed here. Now internally, the expression is really a graph. So you see here at the bottom the x and the y symbolic primitives, and they get added together. So there is an addition node, there's a sign node that takes the result of the addition, and there's a multiplication. And this is how the expressions look under the hood. This is just for illustration. And with these expressions you can do things like get the Jacobian of z expression. So that's what you would do on paper normally. Notice in the printout we have twice x plus y appearing. This sounds a bit weird. Can't we be more efficient? Well, actually what's going on under the hood is there is no duplication. We only have the x plus y node once, and it's reused for the input for the sine and the cosine. So the print might show you something that is less efficient than what is actually going on. So this means sub-expressions are really shared, and we have graphs instead of just trees. And this is a big difference with all the common computer algebra systems like Maple or Mathematica or MATLAB Symbolic or SymPy. They all use trees. Why is this important? Well, if you go to large-scale systems, your expressions will become very large. And if you don't share sub-expressions, then you will have memory problems. So CasADi, the first part of the name, stands for Computer Algebra System. And we do a little bit of this. So for example, this expression, it will evaluate 2y, the x is simplified away, and again a little bit of simplification, not too much. And apart from Jacobian, you can do hashing also. Now that we constructed an expression out of this symbolic scalar primitives, we can create functions of this. And what the function does, it sorts the graph into a linear algorithm. So here with SX function, it takes a list of scalar symbolic inputs and a list of expressions that will be the outputs. So we have given arguments x and y, and this is why in the printout it says 2 inputs, each scalar 1 by 1. The output is also 1 by 1, so scalar. And here is the core of the algorithm. So what CasADi did was sorted the graph and created a simple tape and a set of operations that operate on the tape. So every line is a simple operator working on 2 variables that came before in the tape. And this is the tape where we're actually going to do AD on. Notice the tape indices. The tape is at 0, at 1, but it reuses the 1. So we have a reuse of tape variables. That's just a feature of what we can do in CasADi. What can you do with such a function? Well, we can evaluate it numerically as such by setting the inputs to some numbers. The second argument here is the index for the input. Evaluate it, print the output. So it just gives you a number. There's a shorter syntax like this, where you give the list of numerical inputs. Give the same result. Well, actually, it returns a list of length 1. It's a list of all outputs. We can also mix numerical and symbolic as such. We can just insert a symbol in here, and then the x is replaced by 1.2. Stuff like this. One thing that we can do with such a scalar function is generate C code of this. We generate code. Let's skip a bit through to the evaluate function, and here you see actually this tape that was shown in the printout reoccurring. So this is you could actually compile this and run it on an embedded system where you can evaluate numerically the graphs that you constructed in CasADi. Now let's move on to matrices of scalar expressions. So if we give extra arguments to SXSim, it can take number of rows and columns. So let's construct a 3 by 3 matrix of symbolic primitives. So each entry is a symbolic primitive. We can do operations on this like solving by this would be system inversion, what you would learn in high school, doing Gaussian elimination on A symbolically without pivoting, of course, because everything is symbolic. You cannot make decisions. So you get these large graphs. You can do things like getting a trace. So here you get the diagonal entries added together. You can do matrix multiplication. We can do norms of matrices. We can do a lot of slicing. And this notion of matrices allows you to model your system and to work on your algorithms. So one rule in CasADi is that actually everything is a matrix. The A that we defined before has a shape, 3 by 3, and the Z that I used previously in the previous section is really also just a matrix, a 1 by 1 matrix. We can construct identity matrix with I. So we tend to borrow some names from the MATLAB world. Here you see double zeros in the printouts, and the double zeros are structural zeros. When we take the Kronecker product with the matrix A, we have this nice block structure. So I update my rule and I say, actually in CasADi everything is a sparse matrix. So if I spy this block structure, I get this printout. The A was actually dense, and the Z does also have a sparsity, which is 1 by 1 ends. Now I demonstrate a bit of automatic differentiation, and I will do this by hand of an ODE example. So here you have a description of an ODE with 3 states. Let's introduce time, a control, and then the 3 states as such. And I create an expression which is the vector of the right-hand sides. So it's a vertical concatenation of these right-hand sides. So it's a 3 by 1 vector. And you can take the Jacobian of this, and you see that some zeros are structural. So there is some sparsity detection. So how does CasADi actually compute the Jacobian? It's with AD. How does AD work? Let's demonstrate this. First, under the hood, there is an SX function created for this ODE expression. And then we generate a new function from this original, which does forward sensitivities. And this F adjoint function will evaluate the adjoint derivatives. So let's look at these algorithms side by side. So this is the original F, which took time, a control input, and then 3 states, and evaluated as output the 3 right-hand sides. And then you have the tape here. Now what the forward mode sensitivity function gives you is an extra output, which is the forward sensitivity. And you have 3 extra inputs, one for each original input, which is the forward seed. For the adjoint case, you have 1 extra input and 3 extra outputs, so it's flipped. And what can you do with this? Well, we had the identity, and when you evaluate the forward sensitivity with slices of the unit matrix I, like this, we take a slice of this, and we do this for every column of I. What you get is the rows of, the columns of the Jacobian. So for repetition, let's print out the original Jacobian, and you see here that the rows that were printed here, they make up the columns of our Jacobian. So this is what's going on under the hood. Alternatively, you can do sweeps in the adjoint space. So again, you slice the unit matrix, and this time you get the rows of the Jacobian. In fact, if we know the sparsity pattern in advance, we can do more clever things than slicing only with slices of, we can do better than evaluating with slices of the unit matrix. And for this we use graph coloring, but I won't talk more about this. Let's move on to a demonstration of integrators. So I construct an SX function again as before, but here I use a slightly different syntax. There is no list of inputs. Well, actually it's some kind of labeled list, where I have labels X, T, and P, so that things get a bit more standard, and all the machinery, all the different modules in CasADi know what you're actually meaning. So this is a standard way to define an ODE. And when you print out, you see that the labels are assigned here. So our ODE function has the first input is the state. Then we have no algebraic variables. We have time and we have parameters. Next we'll construct a block that integrates this f over a period delta t. So it starts from initial condition xk and a given fixed input, and out comes the state after integrating it. So how do we construct this function? We say phi equals to integrator, and then the name of the numerical backend that we use, and then the ODE. So CVODS is from the sundial suit. We'll give the function a name. We'll give it an initial guess. we set the input for the initial guess and we evaluate. So here we get the state for one integration interval propagated. Well, this number is a bit boring, so let's do it in a loop. And then we can see really the trajectory of how the integrators evolve the system in time. At this point, we could talk about the second rule of CasADi. I said before everything is a matrix, and now I say everything is a function. Well, everything else is a function. So if we inspect the documentation of CasADi, you see this tree where all classes inherit from functions. So we have SX function, we have integrator, and all of these are CasADi functions. Each function, as you will see, has a number of inputs. It's called the input scheme, with convenient short labels here and description, and it has an output scheme. And by doing set input and get output with the schemes, you can interface any function in CasADi. So let's go back to the tutorial and move on to matrix valued expression graphs. And this is really what makes a difference in CasADi, I would say. So let's do a bit of matrix multiplication that we had before with SX graphs. We construct two dense matrices and multiply them together. What we get is quite a horrible expression graph. It gets complicated. So all the expression is expanded into scalar operations. But maybe this is not such a good idea if your dimension increases a lot, because for every operation you need to store something in memory that describes this operation. So what we have is matrix types. So here I replace the SX by MX, and when I do the multiplication, there is no expansion going on. Instead, there will be a graph of simply two nodes, two symbolic inputs, matrix valued, and then just a multiplication node. So there's no expansion going on at this stage. So this is for efficiency. Another thing is, what if you cannot represent your algorithm into scalar primitives? So if you have a numerical algorithm like a real factorization routine with decisions, you cannot expand this symbolically. So when we do solve on our MX class, we really have this node, a solve node, which is responsible for ultimately doing the factorization of your system. But we represent this just as one node, so there's no expansion. Another thing is for the integrator. We can construct an initial guess which is not numerical but symbolic. So we do this by this. Then we call the phi with an input scheme corresponding to the integrator, x0, and we print the output. And this becomes a graph where there is a function called to the integrator embedded. So the result is still an MX, and we can do more mathematical operations like this. We can make a sign of the final state and add something just for fun. How is this represented internally? Well, simple. You have this symbolic initial value where you start from, and there is a call to the integrator where this input is passed on to the first input, and then the first output is used and propagates to the psi node and addition in the end. And you can differentiate these things actually. If we construct a function, we use MX function at this point, not SX function. It takes a list of symbolic MXs and a list of expressions that are created using those MXs. We can evaluate this numerically as before, and we can take the Jacobian as before. Let me write something extra here. Jacobian expression with respect to x0. So it's a bit horrible. That's one way to do it, working on expressions, but the more clean way is to work with functions. So when we do f dot Jacobian, that is a function created that evaluates the Jacobian. Here you have the Jacobian, and here you have the function value of the original function. So this part shows how you can embed integrator calls into your matrix valued graph. And on this graph you can do derivatives. Actually you can have a look at the documentation where there's a list of all the things that can be embedded in the matrix graph. For example, external libraries. So let's jump to the final part, which is about solving an optimal control problem. So let's focus on this guy first in continuous time. We have a Lagrange objective. We have the dynamic equations as constraints. We have an initial an initial constraint for the states, and we have bounds on the controls. And the two states and the control are decision variables. So what we can do first is remove this Lagrange term and replace it by a Meyer term by introducing an extra state for the cost. This is actually what we did before when I showcased how to do integration. So we have minimize the cost at the final time, and we can write the f that we defined before, our little three-state ODE, have initial constraints and path constraints. And we're going to solve this, for example, with multiple shooting. In a multiple shooting setting, how would it look? Well, you have a lot of decision variables, n plus 1 for the x's and n for the controls. And these are the most important constraints. They do the shooting part of the multiple shooting, or the gap closing. So you say when you integrate xk and uk over one control interval, your state has to end up or has to match the state at the next control interval. And this discrete optimization problem, we're going to cast it as a generic NLP in this form. This is the form that CasADi takes. So first we need to construct a big vector x where all the x0 through xn is contained. And there's a simple trick in Python where we can do this with struct simmx. So we say we need an x, a state, for n plus 1 times, and we need a control for n times. So x is really the stall vector, which is length 83 at this point. And we might as well just have constructed it with mx.sim, but this is a bit easier with indexing. Because now if we want to, for example, evaluate this integrating block for x0 and u0, we have a syntax here that is quite close to the mathematical description. So we move on. I'm going to construct this optimal control problem. So here we have the shooting constraints. How do we construct them? We start with an empty list of constraints and then loop. And instead of feeding numerical values to our integrating block, we feed it with symbolic entries in the loop. And we append to the list the difference between those. So this is how you create the constraints. The objective is simply the cost evaluated time n, last time point, and then here we create an mx function. The mx function will serve as an NLP description, so that's why we use the NLP in and NLP out schemes. So the NLP takes a list of decision variables. Ours is called capital X, and it takes an objective value and a list of constraints. Notice that there's actually two inputs that we could use. There is parameter, but at this point we didn't use it, so we don't care about it. Here you see the integrator calls in the function graph. With this NLP, as I told many times before, with this mx function we can do Jacobian. So NLP.Jacobian xg, it does sensitivity of g with respect to x. If we initialize this, we see that the shape of this Jacobian is 60 by 83. So we have 60 constraints and 83 decision variables, and the structure of our Jacobian looks like this. So this is very typical of optimal control problems discretized with multiple shooting. Very familiar block structure. And in CasADi this is all done automatically. You don't need to worry about this. And now we need to cast it finally into this form. So we create a new function, an LP solver. It's also one of the existing CasADi functions. The backend we use is IPopt, the interior point method solver, and we give it the NLP. We initialize the solver. We set the bounds for the nonlinear constraints to 0, because we only have shooting constraints, and they are equality constraints. And for the bounds on decision variables, we can initialize a numerical vector with -infinity using this syntax. And then we can set for all controls the bounds, the lower bound to -1, the upper bound to +1. And we have a constraint on the initial value, so this is how we do initial constraint. We pass these bounds to the solver, and then if everything is correct, it should give us the answer to the problem. So here you see printout of IPopt. Here it says number of variables 80. Actually it eliminated 3 variables from the problem because they are equality constraints anyway. And optimal solution found, it says. So let's inspect the solution. Well, it's a bit boring. It's again a vector of numerical results. So let's plot this. The trajectories. This is the optimal trajectories, so it's regulating to 0. And the controls that it used are these. So that's actually it for this demonstration. To close, I have a little bit of a teaser, which Greg Horn did a while ago on kite power optimization. So in this video there is an orbit for a power generating kite being optimized. So this is CasADi. This is using CasADi in the background. Of course, the visualization is not part of CasADi. And then for final closure, a bit of distinction with other software that you might know. There is Akedo Toolkit, which is also from our group. So how is it different from CasADi? Well, Akedo Toolkit is actually a black box approach to solving standard form OCPs. While in CasADi, you're not giving actually an optimal control problem solver. No, you write it your own using very simple modular blocks. So that means you have no limitations on how you formulate it. Also, Akedo is geared towards small-scale systems, while CasADi does good with large-scale and sparse and structured stuff. Akedo, I would say, is a bit easier to get started quickly. CasADi is harder, but once you know the basic concepts of CasADi, and I think I did a fair job at conveying those, if you get these concepts, then it's easy to go very far. There is no limitations, and it's also easy to extend CasADi. How does CasADi compare to other AD tools? Well, most AD tools, they have the scalar graphs only, so they have difficulty scaling up to large systems, I would say. They can deal a bit with this, with the concept of checkpointing, but our matrix valued expression graph is actually similar to this checkpointing, but in a cleaner way. And CasADi comes with these batteries included, with the solvers and the integrators. So it's really geared towards optimal control. Okay, thank you for listening.